This video is a review of the 4 tests that we know. 3 of them are for maxes and mins. The other one is just to determine intervals of concavity and points of inflection. I'm just going to show you a quick little memory tool that I saw to remember concavity using the second derivative. So some of you mix up how to tell if it's concave up or concave down from the second derivative. So I saw this once and it might help you. If it's not going to help you, then just disregard this. But we know if the second derivative is positive, that means it's concave up. So some people make this little smiley face with the positive I. So it's the second derivative. So I have 2. It's positive. So 2 positives because it's the second derivative. Concave up. Yay. Happy. Second derivative is negative. We know that means concave down. But just so you don't forget that, let's make 2 negatives because it's the second derivative. 2 negatives and concave down looks like that. It's a sad face. So here are 4 examples for you using every test. We have our closed interval testing. That's the only test that tells you absolute extrema. That's very important to remember. Our first derivative test tells us not only where relative extrema occur, but also intervals of increasing and decreasing. Then we're going to get intervals of concavity and points of inflection. That's no max and min. That's just a test to get the intervals of it. And then we'll do the second derivative test to find the relative max and min values. Notice the first and the second derivative test tell you the exact same thing, just different methods. So pause the video right now. Once again, please make sure this is not on mute and pause your video now. If you don't try these on your own and you just watch me do it, you're not really going to know if you actually know what you're doing. So pause now, try all 4 of them, spend some time doing that. And then you can press play to check your answers. First one is here. For my first test, where am I? Okay, I got the derivative. I need to know where the derivative is 0 or does not exist. Here is setting the derivative equal to 0. This derivative never is non-existent for a trig function. So I found my inverse here. Some people forget their inverses. And I have pi over 6 and 5 pi over 6. This is a closed interval. However, both of these fit in here. So they both work. I get my end points. So this is my left point, my critical number, my right point. And all you have to do is just compare your y values. This is clearly the smallest one. So that's my min. And this is clearly the largest one. So that's my max. And if you look at a graphing calculator, so here's my conclusion. If you look at a graphing calculator and, let's see here, I graphed them. I did a window negative pi to 2 pi. I typed in my function and I graphed it. This is where the absolute min was. Here's one of our relative maxes. Here's our relative min. Here's the absolute max. So these are the 2 values that we stated in our conclusion. Okay, next one is here, so check your work. Hopefully you got the same thing as me. I'm using the first derivative test. Now make sure you look very, very carefully here because my original function does not exist when x equals 0. And I'm going to show you a graph of that because some of you might get confused with what I say at the end. So for the first derivative test, you need your first derivative. There are 2 ways to do it. I showed it to you in your first video on first derivative test. If there's one term in the denominator and more than one term in the numerator, you can do this. Separate it, and then you avoid the quotient rule. The only thing is now you're going to need common denominators, and then you'll have to do more work. I ended up just doing the quotient rule here. I canceled an x right here, and this is my first derivative. I need to know where my first derivative is 0, so I set my numerator equal to 0. Here's 1 critical point. I need to know when the first derivative doesn't exist, so I set my denominator equal to 0. Here's my other critical point. I make a number line of them. So one interval is from negative infinity to 0. Another interval is from 0 to 2. And another interval is from 2 to infinity. So they're right here. This is when I need to do the full-blown table. So I got test points in each interval. I plug them into the derivative. If you get a positive first derivative there, then you know that your function is increasing. If you get a negative first, one second. Hold on, Joe. Okay, sorry about that. Joey's getting impatient here. So if my first derivative is negative, I know my function's decreasing. If the first derivative is positive, my function's increasing. Now look very carefully how I stated this. Increasing and decreasing, that's pretty standard. Notice how I justified it. My derivative's positive, my derivative's negative. I can say that f has a relative minimum right here because right there, and that will be right here, at 2 because the derivative goes from negative to 0 to positive. I cannot say that there is, so it looks like there should be a maximum here because my derivative goes from positive to negative, but that would be at 0. And if you look at your original function, x is not defined there. So the original function doesn't have a value there. And let me show you the graph of it. So x cubed plus, I ended up graphing it here. So I typed in my function, I graphed it, and notice you cannot say that there's a max here. It's going up here and going up here, but there's no actual value there. There's an asymptote. F of 0 doesn't exist. There is a relative min here, though. That's what we were able to say. And let's move on here. Okay, so I'm testing for intervals of concavity and a point of inflection for 1 over the cube root of x. So in order to get to the derivative here, I rewrote it like this. So the way this test works, remember, is you have to set your second derivative equal to 0 or your second derivative not existing. So here's my second derivative. Make sure you understand it. I always write it as a fraction, and I set my numerator equal to 0. This is nonsense. So there's never a spot where the second derivative equals 0. There is a spot where the second derivative doesn't exist. Also notice this is not a critical point. This is a possible point of inflection. This is where I have to do the full-blown table again with my intervals, my test points. I plug them into the second derivative because the second derivative tells us concavity and points of inflection. And if my second derivative is negative, my function's concave down. If my second derivative is positive, my function's concave up. So I am able to state concavity, the intervals of it, pretty easily here. Now, you might be thinking, oh, there's a point of inflection right here because I go from the second derivative being negative to positive. But right here, my second derivative wasn't 0. My second derivative didn't exist. And if you look right here, I can't say anything about when x is 0 because 0 isn't defined in my original function. The function is not defined here, so I can't say there's a point of inflection there. And if you look at the graph of that, let me pause this so I can graph it. All right, so I typed in my function and I'm graphing it. Notice it is concave down here. It is concave up here. The function changes concavity at 0, but it's not a point of inflection because there's actually an asymptote here again. So I cannot stress enough that you need to look at your original function and make sure your x value that you're using is actually in that domain. Okay, so make sure you're all set with that one. And last one, check your work. Hopefully you got the same thing as me for the second derivative test. I have my function here. The way the second derivative test, remember, you still find where your derivative equals 0. I need a flat spot. So on a function, we need flat spots where the tangent line is flat. We don't want where the derivative is not existent because we don't want vertical tangent lines. We want horizontal ones. Then we're going to see what the concavity is at those critical points. So this, whenever I set my first derivative equal to 0 and solve, these are some of the critical points. Then you plug these into the second derivative. So you find your second derivative. Notice the second derivative test is nice. I don't have to do that full-blown table. I actually think the second derivative test is quicker. People in period 2 heard this, but not period 5. Johnny was saying, he was saying that sometimes if we use a second derivative test and we get the second derivative equals 0, we cannot make a conclusion. So there was no conclusion could be made. And then he said it's not very reliable, so why don't we always do the first derivative test? The thing is, the first derivative test might be more reliable and we won't run into this issue where we can't make a conclusion. The thing is, the second derivative test is just so much quicker. All you do is find the critical points and plug them into the second derivative. There's no intervals, no test points. So anyway, I plug in 0, it's concave down, I get a max. I plug in 2, it's positive, so it's concave up, so there's a min. And here's how I state it. Don't forget you need this and this, this and this. Notice the notation, 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 notation. Okay, have a great weekend. Study, study, study.